So let's look at one more section, section 6.7. And by the way, this is the last section that will be included in our first exam. So, which is, by the way, a week from today. So it includes chapter 7 on hyperbolics, inverse trig functions and all that, and these applications to surface area, physical applications, and arc length. All right. So let's look at other physical applications for the integral, and well, let's relate density and mass. And well, for those of you who have taken chemistry classes, you know what density is. It's defined as mass over volume, right? And well, that changes depending on the material, depending on the element from the periodic table or the compound, you know. So, but in this case, well, we're not going to look at 3D because, well, if when you think of density, you think of, well, you're relating mass in volume, but that's not the only one case of density. We also have superficial density and we also have linear density. And for the simplest case, we're going to look at the linear density. For those of you who are going to take Calc 3 next semester, there we're going to look at density again, but now in 3 dimensions because, well, that's what Calc 3 is about. It's functions of multiple variables. We'll look at the 3D space instead of just the 2D plane, which is what we do basically in Calc 1 and 2. All right. So, well, from the formula to find density, usually you use the letter D, but actually it's the letter rho from the Greek alphabet, mass over volume. That's and from there we get mass equal density times volume. All right. So, but again, we're going to take the easiest case in which we're going to multiply density times length. All right. Well, so what's the deal here? Well, so when you have, for example, a liquid or a solid and you're finding its density, well, that chemical substance is uniformly formed by the same substance, so the density has to be constant, right? It's the same value, so that's why we would use just this formula, no calculus involved. However, what if you have a bar, for example, a bar we're made of an alloy of different materials, or in this case, the density is not even at every single point. And that's where calculus comes into play here. Right? So whenever the density is constant, so if we consider a 3 centimeter thin wire, so well, a wire which is for the simplest case, copper, you know, or any other metal that it's a good electricity conductor, you know. So, well, it's copper evenly, so the density has to be the same all the time. So mass equals the density times the length, and the density in this case 4 grams per centimeter times 3, in this case centimeters, and of course checking the units, so that's 4 times 3, which is 12 grams. So the units are consistent with mass, 12 grams. All right. Well, of course, for this course, you're not expected to know any chemistry, of course, because of course we're not going to look into anything from the periodic table, all those properties like molar mass and all that. So that's fine. Okay. So, well, what happens when the density is variable here? Well, so let's consider again a very simple case when we have a wire. This is a wire of length defined by some x equals a to x equals to b. All right? And well, of course, in this case, let's assume that the density is not the same at this point that it is at this point, etc. Because otherwise, if that's the case, like in the previous example, just multiply density times the length, and that's going to give us the mass of that material. So in this case, we are going to consider a really tiny partition. As usual, the same way we do anywhere in calculus, like when we defined the arc length the other day, taking a partition of a length, like when you define the area under the curve for the integral, a tiny partition for a rectangle. So we're going to take this little partition here, and let me call that delta x. Right, that's going to have some increment, some tiny. So in this case, what do we have? Mass, let's take it from mass, equals density times length. All right, but well, in this case, since the density it's not the same all along this wire, so let's just call this m equals some rho that depends on x, depending on the position, on where in the cable, where in the wire, where in the length that density will be variable, and that distance, well, that's going to be our delta x. All right, that increment. And of course, from here, I think you see where are we going to. So now what we're going to do is add all these mini lengths. For example, you can define another length right here, another delta x here, and maybe another delta x here. And of course, again, from the definition of the Riemann sum to define the integral, these are infinitely many. But of course, I'm not going to do infinitely many partitions, right? Just see the picture here, and then from here, just go to the integral. Mass, which is the integral of the given function for density with respect x within the limits a and b. So that's all we're going to do. Integrate a really simple function, and of course we're going to keep it simple. We'll keep this simple because for more complicated functions, that's the next chapter. We will review the integration techniques or all the tricks that we did in Calc 1 for integrating and do U substitution. We're going to learn a lot of new methods to integrate. So, okay, let's find the mass of a thin 3-meter bar made of an alloy whose density is given by rho of x equals 4 plus 8x. Again, it's an alloy. The density, it's not even at every single point. And well, this function is measured in kilograms per meter. That's the density, where x is the distance from one end of the bar. All right, so, and in this case, the mass is going to be the integral of the density function from a to b with respect x. And in this case, well, it's a 3-meter bar, so if we want to find the mass of the entire bar, we're going to get the integral from 0 to 3 and integrate 4 plus 8x with respect x. All right, and well, just to check in the units, this right here is given in kilograms per meter, and this one right here is given in meters. So when we cancel the meters, what are we going to get? Kilograms. Is that consistent with the property of matter that we want to calculate? In this case, mass. Well, mass is expressed in kilograms, amongst other units, of course. And well, in this case, I will just give you the answer: 48 kilograms. By the way, this kind of exercises on the exam, you will be able to use the F and INT. What I'm interested in this kind of exercises on the exam is how you set up the integral. And in fact, I mean, these are going to be like really simple integrals to compute, and so no need to do all the steps. So only for these word problems. So let's see. In case you haven't used the F and INT form before, let me do that integral on the graphing calculator. So So, well, takes a minute. All right. Let me clear. So, okay, so the f and int function under graphing calculator should be found under math. And then you will see a menu here. You have 1, 2, 3, 4, 5 columns. Keep in math. Just scroll up a few times. And number 9 will be the f and int. Click enter. Some calculators are pretty cool and they give you these little boxes to just fill in the blanks. Some other calculators don't have that, don't look like that. If your calculator doesn't look like this, see me at the end of class so I can help you how to set up the integral for this. And well, lower limit 0, upper limit, how was that, 3, and the function is 4 plus 8x. 4 plus 8x with respect x. All right, and just click enter, and that's our final answer. Okay, so again, for the exam questions, for physical applications, f and int is fine. Okay. All right, another application, work. Well, so work it's described by the change in energy when a force causes a displacement of an object. You know, when you push a table, when you push a box, well, it's how much force are you applying on a given amount of mass. And well, of course, we have the corresponding units. The most common ones are newtons, which are defined by, of course, for those of you who have taken a chemistry class or a physics class, these are kilograms, meters square per second squares. Those are the compounded units for newtons, right? And well, of course, the work required to do a task is the force multiplied by that distance. So, for example, if I apply a force of 5 newtons to push this table, which is maybe, I don't know, 20 pounds, let's say. All right? But that's when the force is constant, right? However, that's not always the case. So, I mean, even in the simplest case, when you just push a chair, you start, or when you fall, something heavier, when you push this table right here, there's a point in which you get tired, the force is not the same, so the force is variable, even in the simplest case, right? So when it comes to the simplest case, well, let's determine the work done when a 20 Newton force pushes a cart throughout 3 meters. Okay, well, work equals force times distance, and this force, which is 20 newtons, times the distance, which is 3 meters. And well, 20 times 3, which is 60 newtons meter. Be careful with the units. It's not newtons per meter, because in this case the units are being multiplied. These are newtons meter, or newtons times a meter. Simple calculation, in a very similar for the constant density problem. But again, in the reality of those forces that we apply when pushing boxes, tables, or walls are not always constant. And if you see this formula, it resembles a lot with the density formula from before. So all we have to do in this case is we need to know a force function in order to find the work done. And well, one of the most famous work functions are the Hooke's law. Hooke's law is it's this law that describes when we push or pull springs, you know. And well, so what's Hooke's law? It's right here. The force required to compress or stretch a spring within its elastic limits of force. You cannot pull or push a spring all the way. It's going to break if you get past those limits, of elasticity. Well, so it's proportional to its distance x, that the spring is either compressed or stretched from its natural or original length. And it's a linear function, F equals Kx. Well, what's that K? That K, it's a constant of proportionality that we need to calculate first before setting up the problem to find that work. What does that K represent? Well, it depends on how that spring is designed. It depends on the material of how the spring is built as well. And well, in this case, for the values of x from its natural length, whenever x is a positive number, we're stretching the spring. But otherwise, when x is negative, we are compressing the spring. All right, let's have a look at this one example. So we have a force of 8 newtons that is required to stretch a spring 2 millimeters from its equilibrium length. Well, this is also known as relaxed state. So the spring is there, it's not being pushed, it's not being stretched, all right? It's not compressed, not stretched. Okay, the question is, how much work is required to stretch the spring 4 millimeters from its equilibrium length? All right. So how about we set up an integral first, and then you'll see what we will be missing. So the work done by this force will be from 0 to 4, well, A to B first, F dx, where F equals the force function, that's 0 to 4, but we're missing the K. And of course, we cannot leave the answers in terms of K. We need to find that value of K. So we're going to do some scratch work first. So from Hooke's law, we know that F equals Kx. All right, this sentence right here. A force of 8 newtons is required to stretch the spring 2 millimeters. So that information, we will use it to find the value of K. Well, where have we seen this before? Maybe in intermediate algebra or maybe in pre-calculus when it came to something called variation. Remember direct variation, inverse variation, joint variation? So you started with problems like this where you were given information about all the variables that were involved, and that information was used to find that constant of proportionality in this case. So we're going to use these values. Oh no, that's fine. So a force of 8 newtons is required to move the 2 millimeters away from its original length. So that means K equals to 4. So we may now write an integral right here. The integral from 0 to 4, and that's a 4 x dx. And while integrating this one is really simple right here, so that's going to give us a 32. And about the units, so this is where we need to be very careful. So notice this force is given in this force is given in newtons, but this dx is given in millimeters. So this unit right here will be not Newton meters but Newton millimeters, and that's fine. I mean, you can leave it like this in terms of newtons and newtons millimeters, newtons meters, etc. But of course, if for whatever reason you are working on MyMathLab, you are given the length in millimeters, but in the end they're asking you for the questions I mean, they're asking you for the answers in newtons meters. All you have to do is convert the units, right? So, and I'm gonna do that just to show you how do we do that. Well, so very much like in chemistry, you know, when you do stoichiometry, you want to cancel the millimeters. You want meters, and 1 meter is how many millimeters? Well, not meters. Let me actually do centimeters instead. I think for short springs, I think centimeters are make more sense. So no, never mind. So I want to cancel millimeters. I want centimeters. There are 10 millimeters in 1 centimeter. 32 divided by 2, that's 33.2 newtons centimeter or meter. Well, depending on the units, of course, right? So you would just use the whatever you know, conversion units. Okay. Questions about this one? Yes.
What is the value of K stand for?
The K is it's a constant. It's a spring constant, yeah, and that's a value that depends on each spring. Like for example, this spring in particular was designed with materials and the thickness of the wire that is made from. It was designed to require 8 newtons to be stretched 2 millimeters. So springs vary. Maybe there are other kinds of springs that may need a larger amount of force, like maybe, let's say 32 newtons, just to stretch it 1 millimeter. And well, that's part of the K in this case. It's part of the design of the springs. All right. Okay, how much work is required to compress the spring from its natural length to a length of 6 millimeters? And here is where we need to be very, very careful. Okay, number one, let me draw a little diagram here. Okay, so the spring, its natural length is 8 millimeters, right? And well, this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, let me erase a little bit. Eraser. Just about this. All right, those are our 8 millimeters in our spring. Okay, so in this case, we're compressing this from 8. We want to go to 6. So what is the displacement in this case? So we need to think of displacement here. So we needed -2 millimeters. We need to go back -2 millimeters. And well, this is where the calculation, or rather the setup, might look a little bit weird. So we want, because we're going to use a smaller upper limit, but that's fine. You'll see why. So when I set up work equals the integral from 0 and -2 units away from its natural, because it's compression this time, same force function. Notice something. Notice Hooke's law is a linear function because the power of the variable is 1. When we integrate a linear function, that becomes quadratic. When you get a quadratic function, whether you evaluate a quadratic function at a positive or a negative value, it's always going to be positive. And indeed, it has to be consistent with the situation. Why? Because, well, whether we're pulling or, well, whether we're stretching it or compressing it, we are applying force. The fact that it's being compressed is not happening by itself. Right? That doesn't mean that so when it comes to science, you need to be very, very careful with that. So, well, let me just give you the answer for this one. That's going to give us 8 newtons millimeter. All right. In the other scenario, can I copy and paste? Well, we don't know. Well, in this case, for letter C, how much work is required to stretch the spring from 10 millimeters to 11 millimeters? And in this case, be careful with the limits of integration. A very common pitfall in this kind of problems is to use those numbers as the limit of integration to go from 10 to 11 millimeters. However, we need to take into account the natural length of the spring and take that as our zero. In this case, well, let me draw it again. So that's 8. And well, so in this case we want to go from 8, 9, 10, 11. So it's already stretched. And we want to know so from how many units? That's 2 and 3. All right. So in this case, the integral for work, it's going to go from 2 to 3. Oops. Oh. From 2 to 3 for x, and not literally from 10 to 11, because again we need to take into consideration as our base the natural length of the spring. If the spring were, let's say, 5 millimeters in its natural, the integral would be, okay, how far is 10 from 5? How many units? 5. It would be an integral from 5 to 6 in this case, but because in this case the natural length is 8, to go from 10 to 11 we're displacing from 2 to 3 units away from its natural length. Okay, and well, the integral for this one will be 10 newtons times millimeter. Okay. Questions about these ones? All right. So let's see other types of work problems, lifting problems. So what do we have? What's the situation? What's the situation here? So we have 100 feet length of steel change, weighing 15 pounds per feet. Be careful, because sometimes we think of weight and mass as the same thing, but they're two separate. They're two totally different things. You know, like mass is the amount of, you know, it's grams, kilograms is the amount of matter an object has, as opposed to weight is it's a force due to the gravity force, and it's also expressed in terms of like a density, as you can see from the units here. All right, so it's being pulled from a pulley, and how much work is required to wind the chain onto the pulley. Okay, let me draw a little picture here. So we have a height, so this is y equals to 0. This is y equals to 100, and here's the pulley here. All right, and there is a chain here. Right? Okay, so notice the units, and notice how the weight of the change is given. And notice the situation. So what happens? So when the change, it's hanging all the way from the pulley. Well, it has a weight. However, as we start pulling that change, that chain gets smaller all the time, right? That means the hanging weight is getting smaller every time, okay? So, well, of course, I mean, I could just give you the formula, plug in the value here, set up the function, this, here and there, right there, but it's important, the most important point of setting this up is again going from the idea of the finite element, and then from there, Riemann sums, integral, integrate, find the value. Okay, so let's do the following. Of course, let's see what happens when the change is at a height y, whatever that is. Y. Okay, let me take this finite element. Let me call this delta y. Okay, what's going to happen when I pull, when the pulley pulls the change? Well, of course there is a change. And derivatives or rates of change describe, of course, changes. Right? So what are the variables involved in here? Well, on the one hand, so there is a delta f and a change in y. Okay, so that delta f over delta y, it's going to be, okay, 15 pounds per feet. And if we solve for the delta f, that's going to be our 15 pounds per feet times the delta y. But that delta y happens to be in terms of feet, all right, which cancel out, and in the end is reduced to 15 pounds times delta y. Of course, these pounds later they will be combined when we set up the entire integral to get that work. All right, so because work is force times distance, we need to set up something for the work. Okay, so the delta W, again as a finite element, so involves a force times a distance. The force we already defined, 15 delta Y pounds, times that distance. Okay, so this is the situation. When the pulley has already pulled the change to a height y, so this is y, then there remains 100 minus y to get to the top. All right? So that's the remaining displacement for the chain. And in this case, that's 100 minus y. All right? And well, in this case, we can go from finite elements, get rid of those deltas, and turn this into an integral. W equals the integral, in this case, well, from 0 to 100. Why is it from 0 to 100? Because they want to pull the entire amount of change. All right. Otherwise, if they just want half of it, it would be the integral from 0 to 50. If they wanted only a quarter of the change to be pulled, well, from 0 to 25 or 3/4, depending on the length. Okay. And that's simply 15 times 100 minus y dy. And a quick comment about the units, just to show the consistency with them. So what do we have? This is feet per pound. This distance right here is in feet, and this dy is also feet. So what are we going to have? We're going to cancel pounds, no, not feet per pound, pound per feet rather. Never mind. Okay, so some feet cancel, and in the end, we're gonna get feet pound, which are the units for work. All right. So computing this integral, just use the graphing calculator, use FNINT, that's fine. You should get 75,000 feet pound. All right. I mean, again, like I mentioned before, I could have just given you a formula. Oh, just put 15 for the density of the chain, and put 100 minus y, which is the expression that relates the height of the chain at any value from its maximum height, which in this case is 100. But I mean, memorizing just that, we would be missing the real concept behind, which is taking the usual finite element and then from there get to the integral. Of course, I mean, on the exam, you don't have to show all this work, just show the integral and use FNINT, and that's fine, okay? Let's see what's next. Okay, the next problem. Okay, what happened here? Okay. So what do we have? Okay, we have a leaky 3-pound bucket that it's lifted from the ground to a height of 20 feet at a constant speed. All right? At a constant speed with a rope that weighs 0.1 pound per feet. All right? Notice this is not a mass. This is a weight in the form of a ratio of its mass to the length that remains when the pulley is working. All right, so initially the bucket contains 10 pounds of water, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 20-foot level. So all the work for nothing. I mean, you end up with so you're trying to get water, it's leaking, you get nothing in the end. All right, that's kind of weird, but anyway. Okay, let's draw a picture, of course. So, okay, that's fine. And so this is y equals 0, y equals to 20, all right? And, well, the leaky bucket. All right, that's the leaky bucket. Yep. And, of course, let's show the direction. It's going up. All right? Well, in this case, we need to split the problem in 3 parts. Because in this case, we're considering the work done not only by the rope. That rope now has a bucket, and the bucket requires additional work to take into account to the final result. And also there's water. Even though it leaks and etc., well, that requires work to be lifted. So let's do the first part for the rope. Well, for the rope, first of all, well, in this case, I'm gonna skip the deltas and all that. I'm just gonna write the integral. So, just comparing with the previous problem, we want to take the rope from the bottom all the way to the top of 20 feet. The density of the rope, which is 0.1, and that's 20 minus whatever height, whatever the height is for the rope, right, with the bucket. And well, just use FNINT for this one. You should get 20 feet per pound. Okay? So that's the number 1 part of the problem. Number 2 part of the problem, the bucket. The bucket itself, by the way, without the water. Okay, so here is the thing. As the pulley starts working, the only thing that's, well, so far, the only thing that is going to change is the amount of rope that is left. All right, so the rope is going to get smaller, less heavier, you know. So that's why we need. So that's why in this case, the density of the rope, it's not the same as the process is going. The thing here is the bucket. The weight of the bucket doesn't change unless there's someone, I don't know, doing a magic spell to make the weight of the bucket, make it heavier or lighter, whatever. But that's not the case. So in this case, the weight is constant. The force due to its mass under the conditions for gravity, it's constant. So no calculus is involved for the second part of the problem. So all we have to do here is simply work equals force times distance, which in this case the force, which in this case is 3 pounds, and a distance of 20 feet, and that's going to be 60 feet-pounds. All right, that's number 2. All right. The third part of the problem would be a little bit tricky. Okay, let me try to do this one in slow motion. Let's set up for the water. Okay, and here is the key. Let me highlight the key. Okay, water leaks at a constant rate. Okay, one thing at a time. Rate, it means change. Constant rate, we can relate that constant rate to a constant derivative. Okay, the derivative of what function, of what kind of function is a constant? The linear function, right? You take the derivative of 3x plus 5, the derivative is 3, isn't that a constant? The derivative of 1 minus 4x, the derivative is negative 4, that's a constant. The derivative of 5x squared is 10x, that's no longer a constant value, right? It's still variable because there's an x. So we will define the situation for the water in terms of a linear function. But well, we need 2 elements to get the equation of a line. Number 1, a point, and the slope. Okay, they're not telling us what constant rate. If they gave us what constant rate would be, well, great, we can just use that as a slope and pick any point. But I mean, how do we define those points if this is not even a Cartesian plane? Well, let's create a mini system here with, okay, let's define order pairs, of course, order pairs x and y, which can be time and height, you know. In this case, this will be height for the x, and the y value will be the amount of water. The amount of water. Well, initially, at the beginning, how high is the bucket with the water? 0. It's at the bottom, right? So the height should be 0. How much water is there at the beginning? 10 pounds, all right? That's the first point. The second point, okay, at the point where the bucket is at its highest point, which is 20, how much water is there? Nothing, because it already leaked, right? Okay, so we're going to use those 2 points to find the equation of a line. And, okay, find the slope. From here, find the slope. m equals y2 minus y1 over x2 minus x1. So y2, which is 0 minus 10, and 20 minus 0. So that's going to be negative 10 over 20, which is negative 1/2. All right? And then from here, we can use this loop in any of the points. I'm going to use the first point. So y minus y1 equals m times x minus x1. So y minus, well, actually I'm going to use the second point instead. I think it's easier. Y minus 0 equals m, which is negative 1/2, times x minus 20, which is y equals to negative 1/2 x plus 10. All right? So that's the function that we will integrate for the water. So that's how, and that involves, notice in this case we're already involving displacement and amount of water. So all we have to do is integrate this with respect to y. All right? So the integral, the integral from 0 to 20 of the function negative 1/2 x plus 10. Oh, well, yes, I should have used y, not x. With respect to y, and in this case, this is going to give us 100 pounds. All right? Okay, so now that we got the work for the 3 parts of the problem, we're good to go and find the total work. By adding the 3 values that we just obtained. 20 plus 60 plus 100, isn't that 180? Okay. Questions? All right. So for the last few minutes, so the last problem, it's more like a comment on the units that we typically use. Well, so in this case, notice for the problems that we've been working before, we work with the English system using pounds and feet. But what happens when we use the metric system, which is one of the most common systems that are used? Well, so we need to introduce the gravitational constant, in this case 9.8, what is this? Meters per second squared. However, how about we look at this problem when we come back next week? Let's call it a day